Hello, my name is Minkyu Lee.
My name is Kush Patel.
Alright, we're gonna be talking about our robot, Team 9 robot. First, our task was estimating position and orientation, generating local map, global map, trajectory, generating the trajectory, avoiding obstacles, and robot's supposed to navigate waypoints with an accuracy of 3 inches, and robots should be able to return to the position in 14 minutes. Not in 14 minutes, but while updating the map. So what I'm gonna first talk about is odometry, how we use odometry to know where the robot is and to know what's the orientation of it. So as we learned in the class, within the wheel speed and within the within the encoders, we were able to figure out odometry function from the lab 1. We use odometry to incorporate to where's the robot and to return its position within the GUI. So that's how we figure out where's the robot, and robot color is printed with the purple if you look at the GUI. Next, we're gonna be talking about generating local map.
The local map, we use an IR sensor. We're just mounting it on the front of the robot. What it does, it'll sweep from 90 to 90 degrees from the initial sweeps, and that'll scan pretty much every wall surrounding its front and back. Given that the angle of the IR sensor from the turret, we have an encoder that tells us, because it's a servo motor, we know the exact angle of the encoder. That way we can also figure out the exact location of the wall given the distance that the IR sensor returns, and that will determine the location of obstacles and walls, and then we can update that to the global map.
We'll talk about how do they update to the global map. So we got map position, we know distance from we know wall is how far is the wall from the robot and what's the angle. And now, because from the odometry we know what's the orientation of the robot and we know what is the position of the robot, within those combined together we can update wall location and global map. We also use a line mapping, and I also ended up dividing the line. If the 2 points are too further away from each other, I make them divide each line, so when it doesn't cover up the blank space, when there's a blank space, you recognize the blank space. I also add the correction function, so assume it wrong, and when it updates wrong, when it scans again, if there's a blank space, then it will update as blank space again. Next, we're gonna talk about the trajectory, which is wavefront function.
So we implemented the wavefront algorithm to be able to navigate to the designated location we wanted. The task required us to move to the final goal using 5 waypoints. So pretty much we would update wavefront every time we scan and sweep, and the wavefront would go from the starting location to the waypoint, and then every time it updates, the current location would become the starting location, and it would use the current location to then navigate to the goal location. And wavefront pretty much works as in it designates the goal value as 1, and it increases the values around it, and then goes to the next point and increases the values around it, and pretty much continues on to the current location of the robot. That way the robot just takes a step into a square with a smaller value, and thus it has moved closer to the target.
I'm going to talk about avoiding obstacles. So our robot has capability of avoiding obstacles. When it sees the obstacle, you can see in one of the video in the computer showing the computer vision. So when it sees the obstacle, it kind of treat as same as wall, so it won't go within the wall. We also have configuration space, so whenever it when the wall is occupying the grid, we also make them occupied that 4 grid connecting to that grid. So within that 2 function, we were able to detect wall, we were able to detect obstacles, and we can avoid obstacle while we are heading to next waypoint or going back to home position. We have what we have is called escape function. So when it get blocked off, when it realize there's some obstacle blocking off the path within, like, that's what they think. When for example, when because of our line mapping, it block off all the path and it can't go anywhere, it got stuck in the same position forever loop, then it's gonna have one of the escape function. If I put I, if it's in the same while loop for a long time, what's gonna happen is it's gonna sweep around 360 degrees, and it's gonna update and correct that blank space. So, and after the correcting that blank space, and if it realizes there's a blank space, and it's gonna update to the GUI, and it's gonna tell the robot to run the wavefront again, then we can go follow that path again. Alright.
The robot, our robot overall, we were able to implement the wavefront, the mapping, and everything very effectively. We were able to reach all the waypoints within an accuracy of a couple inches. The return function took slightly bit longer, a 14-minute time, but it was very effective in also waving and also mapping the entire map, as well as avoiding all the obstacles and reaching the destination.
So I'm gonna talk about what was the difference between actual robot and virtual robot. Well, virtual robot, you think it's a perfect world, so odometry works perfect and IR sensor work perfect. But when it comes of real world, IR sensor give you the one of the glitch. So there's because of that glitch, we need to add a filter. And for the filter, we use heavy averaging. If you are interested, we did it the final presentation. I believe there's a final presentation video. So I think that was our presentation. We were able to finish everything. We were able to navigate waypoints within 3 inch within 11 minutes. We can return to the position in 14 minutes within the 5 inch within 5 centimeter from the actual starting point within slight adjust. Alright, thanks for listening and watching our video. This is Minkyu Lee.
This is Kush Patel.
And this was our RBE 3002 final project.